Hi and welcome to another edition of Ordinary Differential Equations. Today we are going to talk about free mechanical oscillations or vibrations. This is a topic that is familiar to everyone, and we talked about it at the very beginning of the semester, and now mid-semester we are going to go back and take a look at this thing in much more detail. So let's see what is the issue. So free mechanical vibration, familiar to everybody. What is the meaning of free here? Free as opposed to forced mechanical vibrations. So if you consider a person on a swing going back and forth by himself, that's going to be a case of free mechanical vibration. But if this person's friend is standing there and every now and then imparts a force on this oscillating object or the person, it's going to be a forced mechanical vibration. So the case that we are going to consider first is when we don't have a variable outside force in the system. At the very beginning of semester we mentioned that this all comes out of Newton's law, F equal to ma, and that immediately turns into a differential equation. Today we are going to talk about this thing in much more detail. We are going to take a look at a situation where the types of forces that are involved in our problem made out of probably some gravity, that's the weight of an object, drag force, we mentioned previously, like when you stick your hand out of the window of a moving car, you feel a force on your hand. That's referred to as drag force. Drag force is proportional to velocity in our consideration, to keep it simple, and it's always in opposite direction of velocity. The factor C here we had before, we have looked at it before, named it as the drag coefficient. So the force of drag is minus drag coefficient times velocity. Spring force, that's a restoring force that you see on things such as a slinky or a garage door opener and so on. Force of a spring is proportional to displacement. The constants of proportionality is referred to as the hardness of the spring, and this one also points in a direction opposite of the displacement because the spring tries to go back to its equilibrium position. Now what we have in mind is a very simple unassuming situation. Let me just take a look at a basic example of this. This is supposedly representing a spring, and this is an object that's going to oscillate in a horizontal direction. Most of the problems we are going to look at, there could be the spring is oscillating in a vertical direction. At any rate, so we said F equal to ma turns into a differential equation. Let's go look at this thing carefully. This force is the total force, which is made out of the drag force, the spring force, and gravity. So if we write F total is equal to ma, then the drag force is minus cv, spring force is minus ky bar, and the gravity, if it's present, is just this w for us. Now, to make our treatment a little bit easier and make the problem faster to solve, we are going to integrate gravity in our consideration so that we move it out of the picture. How do we do that? We write formula ma is equal to minus cv minus k, and then I factor the k here, and I'll have y bar minus w over k. Now what is w over k? This is the weight divided by the spring constant. So w over k is going to be the stretch due to the weight itself. So I'm going to go ahead and take y minus wk or y bar minus wk as my new y. That's going to be displacement measured from the equilibrium. Let me go ahead and explain this thing in a picture so that it becomes more understandable as to what we are doing. So we said we are typically looking at a situation where the object is oscillating in a vertical plane. So here I have perhaps a ceiling or a steady object here, and I'm attaching the spring to it, and that's where it's the tip of it is at this point. This axis that's going to measure the displacement of it, I'm calling it y bar. The origin of this axis is at the tip of this spring. Then I attach a mass to this. The mass is going to have a weight of W, meaning it's going to exert a force of W on the spring. So that mass by itself is going to stretch the spring anyway. That stretch is equal to, by Hooke's law, the weight of this object divided by the spring constant. So the spring is going to be stretched, and now this point we are going to refer to it as the equilibrium position, meaning if you leave the object alone, that's where it's going to stand. Now if we calculate all of our displacements from this position, our equation is going to be a lot easier to handle. That is what our formula is going to be referring to. So now my formula is going to be my double prime, that's ma, minus cv, that's going to be cy prime, and my displacement is going to be measured from this location. It's going to be minus ky. When I bring all of them to one side, I'll have the equation like this, which we have seen once before. Very similar to kind of problems we have been encountering in the last few weeks. We know how very well how to solve it. We know the meaning of all the components of it, and we are going to be quick in solving such problems. Here in this section, we need to know the meaning of all of that solution and the ingredients of the problem itself. So far we know this is the mass, this is the drag coefficient, this is the spring constant. The y0 is going to be initial position, meaning if I take this thing and stretch it to a certain location, y0 is going to be that displacement. Y prime 0 is going to be the starting velocity of this thing. That is, if I kick this thing to go downward or upward, that speed that I'm going to find out, or the velocity I'm going to have, is going to be my y prime 0. So again, just to make sure everybody understands this, in the simple setup, when you take this object and perhaps you start it from here, then the distance from this location to the equilibrium position, that's going to be your y0. Okay. Then if you give an initial velocity to this thing, to either right or left, that's going to be your y prime 0. So in this experiment or demo, you can control a variety of factors here. You can control the mass, damping coefficient, that the quantity that we refer to as the friction or damping, similar terms, that's controlled by this number. Spring stiffness, that's another way of referring to how hard the spring is. And then a variety of other factors can be also controlled in this demo. Let's go back to our setup here. So we understand how the simple physics of this problem connects to mathematics. We are going to go ahead and start solving this problem and see what is involved in that aspect of topic here. So all the problems that you're going to see in this section and the next section are the so-called application problems that are always talking about some kind of a laboratory setup. There's a verbal description of how we are setting something up, and you have to take that information and translate it to mathematics. So translating, the simplest aspect of it is to extract information such as what is the mass of the object, what is drag coefficient or damping coefficient, or any other terminology that's used here. Spring constant, what is that one? What's the initial position? What's the initial velocity? So we have the cast of 5 items to get this problem started. So translating from science to mathematics is going to be our phase 1. In phase 2, we are going to go ahead and solve this mathematical problem. Just like what we have learned in the last few weeks, we are going to go solve this. Typically, and these problems don't stop there. They don't ask for solving the solution. Rather, they ask solution in the context of what is meaningful in the scientific application. So we have a phase 3 of translating your mathematical answer back to a scientific situation and make some meaningful remark about what you find out. So best thing to do is to solve a lot of problems in this section to become familiar with this 3-step process. By the way, very first one is typically referred to as modeling, or the whole set of them is referred to as modeling in mathematics. So here is a basic problem from your textbook. I just have written it down here so that we go through the steps of it and you see what are the things that are involved. As you look at this thing, it looks very different from problems of other sections. You almost see no formulas anywhere. It's just all plain description. And sometimes the students ask for what's the use of what we do. And here in these sections in application problems, that's where we see the uses of our mathematics in a very direct way. However, these sections turned out to be more challenging than the other ones because of that 3-step process that you have to go through. So previous sections were like a mathematical formalism. You're dealing with the formulas from beginning to end, and here a lot more is involved. In fact, the problem is a lot more mature than those mathematical problems. So let's go ahead and take a look at this thing, see what does it mean. A mass weighing 2 pounds stretches a spring by 6 inches. So when you read these kind of statements, you have to look for clues. Every word in this problem is there for a reason. There is no fat to be trimmed. There is no extra words that are in the statement of the problem. You have to be always on the lookout for what does every single data mean and how do you use that fact in your problem solving. Okay, if the mass is pulled down an additional 3 inches and then released, and if there is no damping, determine the position u of t of the mass at any time t. Then find frequency, period, and amplitude. And perhaps find the third time the mass passes through the equilibrium position. So that's a statement of the problem. So very similar to the picture that we had here. We had the mass at the beginning, they attached a weight to it, it came down, and then there's a third picture I can draw here. That's not where we stop. We take this thing and stretch it some. So the mass has come down here now. And we let it go and it oscillates up and down. If there is no damping, this oscillation will never die and constantly go up and down. If there is damping, then the energy is going to be dissipated, the oscillation is going to gradually die out, and then at the very end the mass is going to stop at this equilibrium position. Okay, so we said we have to go through this 3-stage process. Of course, at the very beginning, maybe step 0 of it, you have to have a general idea of what is going on, have the picture of this whole thing in mind, and then you go through this. So we are going to aim at finding these quantities. Some of them are going to be immediate. Some of them might require a little bit of additional work to figure them out. By the way, this is perhaps one of the places in the course there where you need to have a bit of a familiarity with units and conversion from one system of units to the other system. Now, fortunately, in our problems, this conversion issue is not all that extensive, but you still need to be careful about it when you are applying the problems in this section and stay in a consistent system of units. So this is an issue that you have more than likely faced in all your science classes, physics, chemistry, and so on. and we are just going to borrow on the very basic aspects of that and expect the students to actually be able to do some unit conversion. Okay, let's go. A mass weighing 2 pounds. Very strange way of describing something. A mass weighing 2 pounds. What is this referring to? So this is very first clue. A mass weighing 2 pounds. So we said we have weight and we have mass. Mass of an object is a constant. If you are here or you are on the moon, your mass is the same, but your weight differs quite a bit between being on Earth and on the moon. It all depends on the constant of gravity in your location. So weight is equal to mass times constant of acceleration. Well, g on Earth is approximately, we are going to take it, 32 feet per second squared. So that's a system where the length are measured in feet. Sometimes this is described in other systems such as meter, so that will be 9.8 meter per second squared. Sometimes it's described in centimeters. In that case, it's going to be 980 centimeter per second squared. So we look at this problem, we notice that there is pound and inches and so on. So it makes sense that for us to stay with this number, 32 feet per second. But we notice there is a bit of a problem here. Some of these numbers are in inches and this is in feet, and that's the where you have to apply the conversion. Otherwise your problem is not going to work. So let's go back here. A mass weighing 2 pounds. What does that mean? The weight is 2 pounds. Okay, this pounds is the unit of weight or force. So we are given that the weight is 2 pounds. Mass, well, we don't know what it is, and g in this system is going to be 32. So long story short, from here we find out that m is 2 over 32. In this system, that the unit for this mass is typically referred to as a slug, not commonly used all that much, but the mass of this object is 2 over 32 or 1 over 16. Stretches a spring by 6 inches. Okay, what does this refer to and how am I supposed to represent this number? First of all, 6 inches refers to when it says a mass weighing 2 pounds stretches a spring by 6 inches. That's the initial stretch. That's 6 inches refers to this. As I attach the mass to it, it just comes down. Then the next phase, I'm going to drag this thing a little bit further down, but right now it has just come down 6 inches. So that's the very first stretch. Then we go ahead and say, oh, what does that represent here? What clue does it show here? That should be quick for you. So I'm not sure I need to go to my picture or not, but here's a clue for you. What does that 6 inches refer to in the set of numbers we are after? Which number is it that we are after? Well, 6 inches is the amount of the first stretch. So the 6 inches is not any of these numbers yet. It's a common confusion for the students to confuse the first stretch with the second stretch. Further down we says if the mass is pulled down an additional 3 inches. So in the second phase of this problem we have a second stretch here that refers to our initial position, but the very first one is just we are bringing it from this location to this location, and what are we going to use it for? We are going to use this thing to find out how tough the spring is. What is the spring constant? How do we do that? So we go back to Hooke's law. Hooke's law is this. This is a force is going to stretch a spring proportional to the force that you are applying to it. The constant of proportionality is the hardness of the spring. So we are going to go ahead and extract the hardness from here. When we are doing that, we don't need to put the signs in that section of the formula. We're just trying to catch the K. So here we say the force, which was 2 pounds, is going to cause a stretch, so that the stretch is going to be 6 inches. What is 6 inches? 6 inches is half a foot. So we go ahead and write the Hooke's law, put the minus side aside for the moment. So Hooke's law says force of the spring is proportional to how much you stretch it by. What is our force? Well, the force is the weight of the object, that's 2. How much is it stretching by? Is half a foot. So what's my K? What's the spring constant? So multiply by 2, K becomes 4. If you want a unit for it, it's going to be pound per foot. The K is force divided by Y. So if you want to put unit to it, it's going to be pound divided by unit of Y, which is foot. The hardness of this spring is 4 pounds per foot, meaning it requires 4 pounds to be stretched by 1 foot. So we found another mystery aspect of our problem, and that's that K is equal to 4 feet per 4 pound per feet. Okay, next, the mass is pulled down an additional 3 inches. By now we are good at figuring out what is that representing. Additional 3 inches, what is that? Additional 3 inches is the second stretch here. That second stretch refers to what your initial position going to be. That is, you brought the mass further down 3 inches, and now you're going to let it go and it's going to oscillate. So who is this? This is going to refer to as y of 0. Y of 0, 3 inches. And how should I write it? Should I just write 3? Is that right? Take 2 seconds and tell me if I'm right or wrong. What do you think? Is that all I need to write? These are things that make or break this type of problems. You have to be consistent. So 3 inches is, let's simplify, is 1/4 of a foot. That is our y0. So so far we have 3 items captured: m, k, y0. Okay, so we have m, k, and y0. What else do we know? Here we said every word means something. Then released. What is released? Is that a number? What does that mean? Let me see. Here's another issue. I'm claiming when you say an object was released, it's giving you one of these numbers. What number is it that it's actually disclosing to you? What do you mean when you say you have released an object? Well, that's talking about the initial velocity. When you just let something go, it's at the beginning has no velocity. So release simply means y prime 0 is equal to 0, which is fortunate. So our y prime 0 is 0. So if it specifies at a certain speed, we bring that here, but now it's just 0. And if there is no damping, what does that refer to? What was the concept of damping here? Okay, so damping or drag or friction or whatever you want to call it. Here, if we say there is no damping, we have an idealized situation where there is no drag, or it's very minimal. So C is 0. that makes our problem just that much easier. So there is no damping, simply refers to the fact that C is 0. Okay, we have pretty much everything we wanted. We have M, C, K, Y0, Y prime 0. All of them are there. So we have our 5 required items. We can go ahead and solve it. It says determine the position U of t of the mass at any time t. It's quite customary in your textbook that instead of using letters X or Y or Z, just uses the letter U for being perhaps considering all of them equal. Instead of choosing any of those letters, each of them means something specific to people. It's just using letter U so that it can be applied in any kind of a direction. So this is a clue to us. When it says determine, it means I've given you enough data for you to go and translate and make your mathematical problem and solve it. And then it says determine. Determine, so position U of t is, it simply stands for solution that we were talking about before. We are always solving these differential equation for some function. Now that function has a meaning attached to it. That meaning is simply the position, is the position of the mass, and it's called U of t, as opposed to using the letter Y. So we just rewrite our equation with the letter U at any time t. And then it asks all sorts of other questions that we never faced before, but we see that there: frequency, period, amplitude, certain events, and so on. So these are, we said when we are solving this type of problems, we have a third phase where we have to take our solution and still process it and get something out of it other than, okay, here's a formula. People are not after formulas, they are after something meaningful. So let's go ahead and start. So we have we said I had my prime plus cy prime plus ky equal to 0. We have been writing equations like that. So now our m was 2 over 32, or just 1 over 16. So I have 1 over 16, and we said the textbook wants it in U. Well, we go with U. Damping coefficient, drag coefficient, or whatever this one was supposed to represent, that is simply 0. So we don't forget that it is just 0. Rk, how about Rk? What's Rk? Rk was 4 pound per feet. So that's just 4. Well, it's not Y anymore, it's U. And then what else? Well, whenever you solve these problems, you have to choose sense of your axis. You can have it point down, you can have it point up. It is totally up to you. These are all equivalent. Just be consistent from beginning to end what your axis looks like. So I took my axis going down, so when I go down here, when it says additional 3 inches, this is positive. If I had taken this thing pointing upward, when you pull the mass down 3 inches, that would have been considered negative. But now, if my axis is pointing down, this is going to be positive. So next object piece of the puzzle is that U0. We said we are stretching this thing by 3 inches, which is 1/4 of a foot. And then we have U prime 0, which was the initial velocity, which is 0. So we are at the beginning of phase 2. We took our problem and translated it to mathematics. So we have this equation to solve. Now we go apply phase 2. Phase 2, we have to be quick here. We have done this type of problem. We have done a lot more complicated problems before. So we just quickly go ahead and solve this thing. Let's see. Let me ask you to take maybe 2 minutes. That's what is reasonable here. Can you solve this thing in 2 minutes? So you pause this thing and put the solution back together for me and come back in 2 minutes. So I'm going to continue recording while you guys push the pause button and make this thing stop. So I take this, multiply by 16 to make my life easier, and drop this thing away. So I have 64u is equal to 0. Characteristic equation of this thing is simple. R is going to be plus or minus square root of minus 64. We are careful with it and not getting confused with signs and such. How do we write this thing? Best way to write this thing is with complex number notation. Plus or minus 8i. There is no real part because this was ideal situation with no damping. What does that tell me? It tells me u would be exponential of this, which will be just 1 times sine and cosine of this, which is going to play the role of the frequency for us. So we are going to have a cosine of 8t and b sine of 8t. So that's the general solution of this problem, just sine and cosine. We could have guessed it right from beginning, go from here to here. What's a function that when you take two derivatives out of it, becomes minus 64 times itself. When you take this thing to the other side, u double prime is minus 64u. Well, that has to be sine and cosine of 8t multiplied by some as yet undetermined coefficients. How do I figure out my a and b? So so you cross-check whatever you had with what I have so far. If it's not the same, you go ahead, make sure you review that section from prior material and be up to speed with respect to that. So next question, how do I figure out a and b? Well, it's easy. I go ahead and write u and u prime. Let me also take a derivative so that I can apply the second one. So it becomes minus 8a sine of 8t plus 8b cosine of 8t. So what does this tell me? It tells me at time 0 cosine is 1, sine is 0, so this boils down to just a. How about u prime 0? U prime 0 at time 0, the sine vanishes and we have just cosine staying 8b. Well, u0 is supposed to be 1/4 and 8b is supposed to be initial velocity is 0. So obviously that simply means b is 0. So this problem is particularly simple and clean. B got kicked out. We are only left with the u being equal to 1/4 of cosine of 8t. Okay, so this is mathematical solution of the equation we have. This is the equation, is the solution of it. But what is this? What does that mean? This is now called the position. U meant position. So this is the position of the object, and t is excuse me, I wrote it incorrectly here. Let me clean it up. T is inside parentheses. So this is the position. Well, now we need a little bit of a material from our trigonometry. What is the meaning of these numbers here? Who is 8, who is 1/4, and so on. Let me just do a quick review of these things. I'm sure most of you are up to speed with respect to these things, but let's have a sense as to what these numbers mean. Before we go to decimals, let me just say this is referred to as the frequency. Frequency is going to show how fast that oscillation is going to happen. If instead of 8 I had 80, then this thing is going to be oscillating up and down 10 times faster. How about 1/4? What is that? And that is the amplitude. So 1/4 is the amplitude, meaning this thing is oscillating with amplitude of 1/4 foot up and 1/4 foot down, which just 3 inches. So this is going up and down by 3 inches. There is another concept from trigonometry. You might remember, that's the concept of a period. Period is the length of the time it takes for a process to repeat itself. So we say the lunar period is the length of time for a moon to go around the earth and come back to its almost previous position. So a wave takes some time to come back to the position it had. The period is simply obtained by noticing that the cosine repeats itself every 2 pi. So if you run it 8 times faster, it's going to be repeating at every 2 pi over 8. So 2 pi over frequency. So in short, our amp is 1/4 our frequency. There are different definitions of frequency. You're going to see that in your engineering classes later on. Right now, I better stay to just one thing. That number is just our frequency. Period, there is just one definition for that. Period is going to be 2 pi divided by 8. So that simplifies to pi over 4. What's the unit of this? Unit of this is in unit of time. So we have from beginning our unit for time was seconds, so every pi over 4 seconds, okay, almost every 0.8 seconds, this process is going to repeat itself. So what we have now, let's go ahead and quickly take a look at our friend the Desmos. Let me take something. I had some pictures here. Let me erase them. So what did I have? Y is equal to 1/4 of cosine of 8t. Now this is a little bit small, so let's magnify it. So what was 1/4? 1/4 is 0.25 is the amplitude. So this is just to make it perhaps clear, it goes as far as high as 1/4, that black line. It goes as low as minus 1/4, the red lines. That's high and low. So the distance from the midline is called the amplitude. Okay, and then what else? What is 8? 8 is how many oscillations we are going to have. That's the frequency. The period we said was 2 pi over 4. What's the period? Period is the length of time it takes for a picture to repeat itself. Easy way to see that is from one high to the next high, or from one low to the next low. What is the next high here? You see it's almost it's flagging it for us, pi over 4. The next high is at pi over 4. Next high after that is pi over 4, and so on. So now when this object oscillates, this is going to be one extreme, then it comes and passes through the equilibrium position, the first position here, and then goes to the other extreme. Then it comes and passes the equilibrium position again, and then next extreme. This one, you notice 5 pi over 16. That's the third time it's passing through the equilibrium position. So sometimes the problems ask you for the first time, second time, third time, that the object is at the lowest point, at the highest point, at the equilibrium point, and so on. So you can reason out your way to the solution of these type of problems. Let's go back to our problem here. So we found the requirements that problem wanted from us. This was a particularly simple one because there was no damping, and also there was no initial speed. So other problems, there will be a mixture of sine and cosine, or perhaps there's going to be an exponential involved as well. So the problems gradually become more complicated, and we are going to look at more examples of this in the future lectures. Okay, until then, good luck and God bless.